is a world unto its own. Vast oceans that make up 3/4 of the Earth's surface. And above, oceans of air. It is a world of relentless energy, grandeur, mystery. Man has always sought to unlock its secrets, but unlike the more hospitable land world, this world yields its secrets more slowly, demanding the most ambitious of efforts. But man needs to know. This world has been a source of his food, the birthplace of weather systems that sweep across the continents, a pathway for commerce, a turbulent and unpredictable field of combat, and today, an environmental battleground. The study of the dark, cold world beneath the sea, the interface of the sea's surface with the atmosphere, and the atmosphere above the oceans, all of this is the realm of naval oceanography. The history of the United States Navy is not only a history of sea battles, but also of scientific discovery and technological innovation. Achievements of naval oceanography are woven throughout that history. It began with clocks that didn't keep time very well, and charts that were not always accurate. Time and place, information essential to any mariner. Knowing where you are on the face of the globe is the initial step in studying the sea. In 1830, Lieutenant Louis Goldsborough sent a letter to Secretary of the Navy John Branch, proposing that a system be established to ensure the proper care, storage, and issuance of accurate nautical materials for the Navy. The need was obvious. Increasingly, the United States Navy was assuming a more important role in maritime commerce and the nation's foreign policy. In December 1830, the Navy Board of Commissioners established the Depot of Charts and Instruments, headed by Lieutenant Goldsborough. The seed for developing naval oceanography was planted. In 1837, under Lieutenant Charles Wilkes, the depot undertook its first survey and produced its first set of charts. In 1838, Wilkes was selected to head the first United States naval exploring expedition. With 6 ships, Wilkes set out on a 4-year journey around the world. He surveyed more than 250 islands, mostly in the Pacific, explored the rivers and coast of Oregon, and sailed all the way to Antarctica. On January 30th, 1840, after Wilkes viewed a range of snow-covered mountains from his ship, he wrote, "We saw the land gradually rising beyond the ice, and now that all were convinced of its existence, I gave the land the name of the Antarctic continent." In 1842, Lieutenant Matthew Fontaine Maury became officer in charge of the Depot of Charts and Instruments. Maury set about studying old ship logs and collecting additional observations. From the information he gathered, he published in 1847 his Wind and Current Chart of the North Atlantic and 8 volumes of sailing directions. He created a controversy by suggesting that mariners who followed his charts could cut significant time from ocean voyages. When a ship using Maury's charts considerably shortened its voyage to Rio de Janeiro, the value of Maury's work was proven. Soon, ships were saving an average of 47 days in a voyage of 180 days from New York to San Francisco. Enthusiastic mariners from around the world began sending their observations to Washington, and in exchange, they received Maury's charts. As important as this was, Maury dreamed of systematic international cooperation. In 1853, an international conference on meteorology adopted Maury's method as a common system for logging weather and sea conditions, a major step in the development of naval oceanography. Maury also produced the first chart of the floor of the Atlantic Ocean, which was of great value when in 1858, the first telegraph cable was laid between the United States and England. Faster communications would play a key role in the future development of both meteorology and oceanography as sciences. In the 1860s, as the nation was rent by civil war, naval oceanography was about to enter a new phase. The first of two new inventions appeared that changed forever the face of naval warfare. The demands on naval oceanography would be significant. The first invention was the submarine. The Confederate submarine Hundley was the first submarine to sink a warship, the Union ship, the USS Housatonic. In 1895, the Navy's first commissioned submarine, the USS Holland, was launched. It could dive only 75 feet and lacked one item that would distinguish submarines for over half a century. The Holland had no periscope. The German U-boat of World War I demonstrated its threat to freedom. This threat, as well as the earlier sinking of the Titanic, set off one of the most urgent research and development programs in history. The aim, a method of detecting underwater objects by using sound signals. Early methods of sending sound through water were primitive. But by 1922, a new deep water sounding device developed by the Naval Research Laboratory was installed on the USS Stewart. On an Atlantic crossing, it made a remarkable 900 soundings, resulting in the first sonic profile across an entire ocean basin. The second invention that so changed naval warfare was truly an ugly duckling. On December 8, 1903, Samuel Langley's aerodrome skids off its launch and into the Potomac River, convincing most Americans that man was not meant to fly. But 9 days later, the Wright brothers changed people's minds forever. It happened at Kitty Hawk, North Carolina. For the Navy, the significance of Kitty Hawk was realized 6 years later when Eugene Ely flew a plane off a wooden platform on the USS Birmingham. But could a plane land on a ship? 2 months later, Ely landed a plane on the USS Pennsylvania, creating a vast new dimension of sea power. World War I introduced new weapons. Their effectiveness depended greatly on the weather. Therefore, more accurate weather forecasts were needed. In 1917, Assistant Secretary of the Navy Franklin D. Roosevelt asked his friend Alexander McCady, director of Harvard's Blue Hill Observatory, to establish a naval organization to study weather. The Naval Aerological Service, established in 1919, celebrated its official status with an historical achievement. Supported by the latest meteorological information, the NC-4 Navy flying boat made the world's first transatlantic flight from Newfoundland to Portugal. With the rise of naval aviation, thousands of naval pilots learned to land their craft on what must have looked like a postage stamp in the ocean. It was not without difficulty. Increasingly, one thing was evident. The need for up-to-date weather information was essential to naval aviation. By the late 1920s, aerological units were regularly assigned to carriers and flagships. The age of the floating airfield was here. Air mass and front, two revolutionary concepts developed by Norwegian scientists during World War I. The frontal weather concept was so named because advancing weather systems seemed a battleground, much like the then raging Western Front. It was a concept that changed meteorology from an art into a science. Francis W. Reichelderfer, a Navy pilot and meteorologist, immediately recognized the validity of the Norwegians' work and was instrumental in adapting their concept to Navy needs. Today, Commander Reichelderfer recalls those days.
Before the Norwegians began their intensive scientific research in meteorology, there was no concept of air masses as a dominant factor in causing weather. For example, over the Arctic regions, the air is extremely cold. Every few days, a huge mass of this air breaks off and moves southward. It runs into warm currents of air from equatorial regions. When the cold air and the warm air meet, there is turbulence and conflict. The Norwegians called this zone of conflict fronts. By knowing what the air masses and the fronts are going to do, it was possible for us to be much more accurate in the prediction of weather. We learned we had to consider what was happening on a grand scale in the upper atmosphere, high above the ground, and not just concentrate on the individual storms. Soon we had the Naval Meteorological Service reorganized, and our petty officers were drawing fronts and air masses on their weather maps every day. The significant thing for the Navy was that we could tell what storms would do at sea where there were no networks of weather stations such as we had on land. But our experience in World War I, both in the air and at sea, showed that there was a great need for trained weather officers. After the war, most of the full-time meteorological officers resigned from the Navy, and eventually there were only two of us left, of which I was one. But with the support of the Navy, we persuaded Harvard University and MIT to establish full-time courses in meteorology at the graduate level. This was the first time that graduate level courses had been established in meteorology at any university in the world.
Nearly a century after the expedition to the Antarctic by Lieutenant Charles Wilkes, Commander Richard Byrd spent the winter alone in this hut, 123 miles from his Antarctic expedition. A few years earlier, Byrd had become the first man to fly over the South Pole, bringing the air age to the Antarctic. The serious scientific work accomplished by Byrd's expedition was significant and laid the foundation for Project Deep Freeze in 1956 and the establishment of a permanent scientific laboratory at McMurdo Sound. World War II demanded a knowledge of the ocean environment more sophisticated than ever. Air operations in the European and Pacific theaters and the amphibious landings from Guadalcanal to Normandy vividly demonstrated that in naval warfare, meteorology and oceanography must be considered as one discipline. Wave and tide conditions, wind speed, cloud cover, and coastal irregularities. All of these affect naval operations. In the battle for the Far East, the application of the Norwegian frontal system concept proved vital as the Allies tightened their grip on the Japanese island chain. Teams of American naval weathermen were sent into remote areas of China and with the Chinese established a weather reporting network. These field stations sent weather observations to the Weather Central, or clearinghouse, at Chongqing. By analyzing the moving weather system over China, meteorologists could provide more accurate weather forecasts for the operational area of the Far East. In Europe, accurate weather analysis was vital to the invasion of France. D-Day, originally planned for June 5th, 1944, was postponed one day because adverse weather and wave conditions were predicted on the Normandy beachhead. In the struggle for control of the Atlantic, the submarine played a key role. Sonar beams by which a ship could detect submarines, or vice versa, were bent by layers of water of different temperatures, often preventing the sonar from indicating a vessel's true position. The development of the bathythermograph by Navy scientists gave ships and submarines an instrument which could quickly measure the temperature of the water column. Now sonar operators had the information they needed to judge how their sonar systems would function under various conditions. But sonar operators were confronted with baffling sounds. Mysterious sounds caused anxious operators to wonder what the enemy had devised to distort our sonar. The sounds were found to come from creatures of the sea. Using highly efficient underwater microphones, scientists were able to identify which sounds were made by what animal. These studies help mariners predict noises likely to be encountered in a given area. Navy studies also showed how sonar is affected by the nature of the sub-bottom, its hills and valleys, as well as the sediment that lies on top of it. Sediment charts were developed for use by submariners and anti-submarine personnel. The elation at the end of World War II was soon tempered by uncertainties of a new age. The extraordinary leap forward in science and technology, spurred by the all-out war effort, continued in order to meet the demands of a supersonic electronic nuclear age. To investigate unusual phenomena at high altitudes and probe the physics and chemistry of the upper atmosphere, Project Skyhook sent sophisticated instruments higher than ever before, as well as developing an intricate system of telemetry for tracking these instruments. The cold, thin atmosphere in which these instruments had to operate required the development of technology basic to the coming space program. January 17, 1955. A startling message from this submarine to her escorting tug, underway on nuclear power. The submarine Nautilus marked a technological revolution equal to that of the introduction of steam. The age had come for submarines to go deeper, faster, farther. The missile age demanded more precise navigational information than ever before. To establish the exact position of a submarine and to guide a missile accurately to its target, two natural phenomena have to be considered: gravity and magnetics. The Earth's magnetic field is constantly changing, and the strength of its gravitational field is influenced by the shape and composition of the ocean floor. Aircraft of the Naval Oceanographic Office, equipped with gravity meters and airborne magnetometers, are continually surveying the oceans to provide updated information on the Earth's gravity and magnetics for the fleet. wherever it is. In 1960, with the dive of the bathyscaphe Trieste into the Mariana Trench, a new era in deep-sea research began. For the first time, man descended into the deepest part of the ocean, nearly 7 miles down. A whole generation of submersibles and robots followed, incorporating new designs and materials to carry out increasingly demanding research missions. And now that man was working and living in the ocean depths, deep submergence rescue vehicles were developed to aid and evacuate the crew of a disabled submarine. The space age not only took man to the moon, but gave him a new and spectacular view of his watery planet. In keeping with the scale of the ocean itself, satellites give man a grand view of the oceans. They are the most significant data gathering tool yet to be offered oceanographers. Finally, man can evaluate almost instantly all the complex features of the ocean environment in relation to each other. He can study how temperature affects currents, how currents affect waves. Using infrared imagery, satellites measure the temperature of the ocean's surface, revealing the location of eddies of warm or very cold water. Because sonic waves are distorted by the frontal areas, submarines use such areas to conceal their position. Location of these frontal areas is an essential part of anti-submarine warfare. Satellites also help ships navigate safely in polar regions. Enhanced satellite images reveal not only the movement of polar ice, but also its thickness. The white areas in this display denote thick, impenetrable ice. In 1978, the Naval Oceanography Command at Bay St. Louis, Mississippi, was created to oversee the Navy's consolidation of meteorology and oceanography into one discipline. Its mission, to gather through its far-flung network of ships, planes, and shore stations environmental data on the ocean from the sea floor to the upper atmosphere and predict conditions throughout the world in support of fleet operations. As a part of this command, the Fleet Numerical Oceanography Center in Monterey, California, is the direct descendant of the Navy's early weather central concept developed prior to World War II. By 1950, the first step away from the time-consuming hand plotting and analysis of weather information was taken. With Navy support, Professor John von Neumann of Princeton and a team of prominent scientists developed for the first time a method of using a computer to analyze the complex dynamics of weather information and movement. Compared to modern computers, this was an electronic dinosaur with 18,000 vacuum tubes and 70,000 resistors. Yet it automatically produced a first successful 24-hour weather forecast, pointing the way to a numerical weather prediction system with its modern nerve center at Monterey, California. Underlying this system is the understanding that the ocean and the atmosphere are a coupled environment, affecting each other directly. The center has the capability of receiving data from 3 satellite systems simultaneously. Information on sea surface temperature, wave height and direction, ice conditions, and vertical temperature profile of the atmosphere. A sophisticated data processing system takes the millions of bits of digital information stored in computer banks and displays them in usable form. What emerges from these continuous calculations is a worldwide forecast of the ocean environment, which can be flashed to the operating fleet throughout the world. These forecasts, like the coastal and deep ocean surveys of the Naval Oceanography Command, improve the effectiveness of our Navy, and the command's routing techniques for aircraft and ships reduce transit time, thereby conserving fuel. Today, naval oceanography is a broad but interlocking complex of scientific disciplines. It has progressed into a global science with tools that enable us to go far into space or to the depths of the sea to observe and work. The United States Navy is engaged in a continuing effort to understand this last and greatest frontier of our planet, and in a quest for knowledge that will improve the quality of life for all mankind.